how can we go further now and let's say go beyond transport measurements? And we can go beyond the transport measurement by using this kind of architecture, which is a Coplanar waveguide cavity. And I'm going to now switch gears to these kind of things. So the primary thing which people want to do in this kind of, so now I'm doing a second introduction, is essentially goes back to the, let's say, to the study of light-matter interaction at the most elementary level, which is cavity quantum electrodynamics or circuit quantum electrodynamics. So this is an example which we like very much in Paris, especially in Paris downtown. And this is, of course, an example from the Yale group back in 2004, where essentially the Rydberg atom there is replaced by here Cooper pair box, or more recently Transmon qubit, embedded in the Coplanar waveguide cavity. Here are the mirrors of the cavity, and this is the central conductor of the cavity is the waveguide, guiding the photons. But both these systems, although they look differently, they're both described to a great extent and to a very accurate degree by the Jaynes Comics Hamiltonian. Here I forget about the bath, but I have a spin here 1/2, let's say. Of course, I have many other complexities because I'm a multi-level system in this kind of things, but to a great extent, it's a two-level system. I have a photonic mode, and this is the coupling term. And one particular interesting regime, which I will not discuss you today, but if you had the seminar by Jason Peta last year, he talked to you about this regime in greater details. So we also work on that, but this will not be the topic of today. And very interesting regime is when you have the strong coupling regime, where the coupling strength here exceeds the dissipation of photons in atom. Okay, so again, so here are cavities. So these are, it's barely visible, but you see the photon here, it's in gray. I like gray color, but it's barely visible. It's a Coplanar waveguide cavity. The fundamental frequency of this cavity is in the 6 to 10 gigahertz range. Our quality factors are about 15,000. And we carry measurement at 20 millikelvin or 250 millikelvin. Do you see the?
Yeah,
it's faint.
You can see big enough.
And so our atom, in our case, there are two kinds of atoms. So they're first, let's say, the closed system, which is an artificial molecule. It's a double quantum dot. So this is what Jason talked to you about. So this is very interesting for quantum information. And I will be more interested in an open system when you have a single dot strongly coupled to the reservoirs, which allows us to revisit and to study in a controlled manner impurity physics in condensed matter. I'm running late. So, and this is what I will be dealing with. And essentially in this kind of system, I can do two things. In the closed system, I can induce with the photons transition between the left and the right, essentially. And let's say in the open system, I can study transition between the dot, let's say, and the leads. And this is how we describe the electrical coupling of all these systems to the cavity. Essentially, we can write it's a kind of a density electric field type of coupling. You have the density here of electrons, which couples linearly with the electric part of the electromagnetic field. And so, since we're dealing with mesoscopic objects, the dipole corresponding to this kind of transitions is very large because of the mesoscopic scale is around 10 to 100 megahertz. And this is, of course, why circuit quantum electrodynamics, or one of the reasons why it's so efficient is because you have very large dipoles. Okay, so now, as I have shown you at the beginning, we can study things in transport, but now we'll have another knob, we'll have the cavity, and so now we need to understand what the response of the resonator will be and what the resonator measures. So this is what, if you have a kind of two-level system or a doublet, essentially the resonator response will measure the peaked charge susceptibility. So there is one doublet frequency and there is a peak. And this doublet will measure essentially, will be seen in the real part and the imaginary part of the susceptibility, which affects the transmission amplitude and phase of the cavity. From a linear response argument, you see that essentially you have a Lorentzian line shape, which is this is amplitude here. And by, let's say, linear response theory, you see that the chi here appears here. So, and then you can study this. I mean, this was, of course, studied by us here and there, and also by the groups in Zurich and in Princeton, and also from more recent papers in Princeton, essentially this thing here. But now, when you're dealing with some more open systems, and one particularly interesting regime is when all the energy scales of the system are much larger, so the system is much faster than the cavity photons. In this case, you might think that the conductance it measures essentially the same as the conductance, but it's not true. What it measures is that it measures the compressibility of the system, because the cavity, what it does, it molds essentially, it changes adiabatically the chemical potential of the conductor, and this measures directly the compressibility of the system. Again, essentially the charge susceptibility of the system becomes directly the compressibility of the system. And so which means that the cavity provides a direct access to the compressibility, a direct measurement of the compressibility. And the compressibility is particularly interesting when you have electron-electron interactions, when you have correlations. And my favorite correlation system is the Kondo system. So this is the historical Kondo effect. You have an increase in some magnetic alloys of the resistivity at low temperatures, because essentially the magnetic impurities couple, form bound states in the singlet state, in the simplest case, with the conduction electrons. But the most, the modern way of looking at this problem is through its connection to the Anderson model of a magnetic impurity. You have a site with strong Coulomb repulsion, which forbids the double occupancy, coupled to fermionic reservoirs. And this can be mapped onto an impurity problem, a magnetic impurity problem. This was shown by Schrieffer and Wolf in the 60s. But even more interestingly, this kind of system can be now emulated or engineered with quantum dots. And which means that this kind of physics can be studied by looking at transporting quantum dots. And for example, there is people have studied this in transport with exquisite details in different kinds of systems, etc. There is a pretty good understanding, but still a lot of surprises in this phenomenon, also in transport. But there is one thing which was not, I think, no, that's okay. One that's not directly observed is when we consider the processes which build, this many-body resonance, which is a Kondo resonance, which appear in the transport as a peak in the conductance. It's essentially, if you look at these virtual states, which which are built in essentially the Kondo effect. Let's say you start with a spin up in the energy level and a spin down here. Essentially, you have two kinds of virtual states possible, which are forbidden by energy conservation, but allowed quantum mechanically for a small amount of time. So this spin can jump here and empty the dot, like this. This is one intermediate state. Or this spin can jump there because it's the opposite spin here, and fill the dot at large u. And there is one particularly interesting process where the opposite spin from the previous spin jumps on the right reservoir. And so you see in this, so the charge in this process has not changed. The charge is the same here and here, whereas the spin has flipped. Okay. So if you consider, and more importantly, you have a charge here which has flown from the left to the right. So you understand two things. First, that this kind of process, if you build this process at many orders, will essentially can combine together resonantly, and that they will also contribute to transport, as you see here for this simple cartoon. That's a simple cartoon. Then you need to work out, the whole, many body theory, but this is essentially the idea. And what important thing is that when you're measuring now current flowing from the left to the right, you think you're measuring a charge current, a net charge current, but in fact what you're measuring mostly are spin fluctuations because the charge here is completely frozen. And even though this leads to a peak in the density of states, it's a peak of primary spin fluctuations essentially, and not and so the question is whether it's possible to observe this decoupling of the, let's say, this freezing of the charge dynamics, which shows you that the Kondo resonance is definitely not a resonant tunneling process, or it's like some kind of many-body resonant tunneling process, if you will. So, and the cavity is in fact very well suited to do that. So here is again now the system. Now we have a nanotube which we embed in the microwave cavity. So we have two like normal contacts. We have a bottom gate which goes, one side goes to the central conductor of the cavity. This allows us to have a large coupling. And the other side is to control this to the DC part of the gate. And essentially we measure the transmission through this cavity. So the measurements are done at 250 millikelvin. So it's not in the quantum regime from the cavity, but it doesn't matter. And essentially the frequency, the phase shift of the transmitted amplitude measures the frequency shift of the cavity resonance frequency, and this allows us directly to measure the compressibility. And of course, simultaneously, what we can do is measure the conductance through this device. So the interesting thing with nanotubes, but like in any other quantum dots, which is very often, is that you can essentially change the transport regime continuously by just a gate knob from the Coulomb blockade to the like the Kondo regime, because you increase the gammas to the reservoir. And essentially, this is very useful for us because this allows us to calibrate essentially the electron-photon coupling strength. Because the Coulomb blockade is a very well-known phenomenon in which you have interactions but no correlations. So here is the conductance. That's a conductance cut here as a function of the gate. You see peaks here in the conductance. These are Coulomb blockade peaks. And you see that in the phase of the transmitted microwave signal, we have perfectly correlated peaks in the phase. Okay? This is normal. It's because each time you have a charge, a conductance, the charge is allowed to fluctuate, and therefore it switches on the dipole, let's say, and therefore you have also a finite measurement, a finite phase shift, so finite compressibility, and that's normal when you don't have correlations. Essentially, compressibility, conductance, that's the same. That's roughly speaking the density of, say, the Fermi energy. So in fact, you already see that this is a tiny compressibility because this phase shift here corresponds to a charge sensitivity, the noise here of 2 × 10⁻⁴ electrons, because you have a very small density of state, essentially. So if I compare, the compressibility contrast is some 7 orders of magnitude smaller than the piece of metal of 1 micron cube. So this allows us to couple to calibrate the coupling strength. So now let's see that what we have in the Kondo regime. So we crank up more the gate, and you start to see here here ridges here, which are, if I do a cut, I see a peak at 0 bias, which is the Kondo resonance. But if I look at what's going on, this is in blue here, and I have bumps here, which are pretty broad, which are charge fluctuations. But if I look here at what's going on in the phase contrast, this peak is completely absent. So this means that this peak here, although I see it in the conductance, and therefore it's in the spectral density of the system, it corresponds to a frozen charge because the charge is not allowed to fluctuate on this peak. So this is a direct demonstration of the fact and a direct observation of the frozen charge of a Kondo resonance. And it's very well reproduced by the numerical and renormalization group. In particular, what you reproduce also is that there is some shift between the two bumps. So you see, at large energy, now it's comparable to the charging energy. So the charge is allowed to fluctuate. And therefore, you still recover both in the conductance and in the phase signal these two bumps.
Takis, just to clarify, so you're saying that because the charge is not allowed to fluctuate, and the micro response is sort of probing a gradient, Is that
it's another way of looking at that, yeah. Essentially, you need the susceptibility, yeah, exactly. You need the susceptibility because you need two places where the charge will move, and therefore it's a gradient, absolutely. It's the electric field, and therefore the gradient of the potential, which, exactly. That's another way of looking at the problem. Absolutely. So this directly demonstrates to you that Kondo resonance is definitely not the same as a resonant tunneling or some complicated resonant tunneling, that really many body physics is taking place. And we can, look at the temperature dependence and also just confirm this picture. Okay, so as a conclusion of this, let's say, second part, so I have shown you that by doing a microwave measurement, so by coupling a quantum circuit with a microwave cavity, you can see things which were not readily accessible in transport. And in particular, that this has led us to observe, I think this is the first time, the freezing of the charge dynamics underlying a Kondo resonance, which is a very important aspect of the Kondo model. So, and the perspectives of this setup are, of course, the general probe of transport in mesoscopic circuits. Of course, some hybridized light matter, coupling with quantum dots. And we could also imagine to do some kind of quantum simulation of fermion-boson systems in that kind of circuit. And so now, just the last slide is to show you that now we can reconcile the first part of the talk and the second part of the talk by showing that how we could probe, this is a theory proposal now, these specific properties of Majorana quasi-particles with a microwave cavity. And this is a representative proposal which we did with Audrey Cotet and one of my students, Mathieu Dartiaille and Benoît Dussault, is in fact that this device which I have shown to you was in fact already embedded in the microwave cavity. So in the lab, whenever we have something, we see something, we put it in the microwave cavity, in fact. And in fact, the idea is that now if you have excitations which are their own antiparticle, this will impose selection rules on the doublet. You would have a doublet. For example, imagine you have two Majoranas, they come always in two pairs, and then they slightly overlap. You will have then a doublet because you have a repulsion of the levels. They will not lie exactly at zero energy. But so you can say, okay, but then I would see this transition in the microwaves. Exactly, I would have absorption for a molecule or for a two-level system. But since this doublet is built from particles which are their own antiparticle, you have a selection rule, essentially. You have a polarization degree of freedom, which forbids this transition. Therefore, you cannot see this transition. But if you have even a tiny continuum coupled to this guy, you will have photon-assisted tunneling processes which will occur at half the energy of this transition. And the fact that you see something at half the transition which you can characterize by transport would be a smoking gun of the particle and antiparticle duality of Majorana excitation. So this is this sketch here. Okay, and with this, I'd like to thank you for your attention, and that I have been a bit long in my talk. Thank you again.
You couple the RF to the gate or to the source drain? Because architecture uses coupling to the source drain.
Absolutely, yeah. So, in fact, if you couple to the source drain in a very closed regime, there is not so much difference. So maybe I can show. So what we do, let me just see. No, I don't have this line here. In fact, in Jason's, let's say, geometry, if you have, let's say, a closed system, if you have a closed system coupling to the source and drain and doing nothing, essentially, it's essentially the same as coupling asymmetrically to the left gate to the right gate. This is what we do in our cavity QED architecture with the double quantum dots. But if you want to do a compressibility measurement, it's absolutely essential not to couple to source drain, because if you couple to source drain, you will start to see dissipative effects related to the Kondo resonance, for example. And so one of the difficult part of the experiment was actually to engineer this gate coupling, and only the gate coupling, and to be sure to find experimentally means to prove that this is mostly the gate coupling. So this is what Mathieu Desjardins did And this is how he came up with this idea of this bottom gate, which is closed very close to the nanotube, and which couple, you see, you have a capacitively coupled fork, which goes to the cavity.
You have a separate DC gate coming from
Absolutely, yeah, from the other side.
So here is the nanotube sitting on the aluminum oxide, or is it?
Yeah, on the aluminum, it touches slightly, yeah. No. Yes, exactly, so this is why. So in the other set of experiments, we have even a top gate with aluminum oxide on the top, which is even here closer, if I say, because here it's not all the nanotube touches the aluminum oxide, and we get even larger coupling strength. And if you do the microwave, let's say, simulation with HFSS, for example, you see that this is probably this is a good way, although we still do not, I mean, to fully understand in this geometry why in some samples we see a coupling, while in some other samples we don't see a coupling. But when we see a coupling, it's a large coupling. Whereas with the top gate, we'll always see a large coupling essentially to the. So this is absolutely crucial to have a gate coupling. So in this particular device, we can estimate that the gate coupling was at least 100 times larger than the source drain. There is a residual always source drain coupling, but which we don't see.
Due to parasitics.
Due to parasitics, because the field, you see, it goes, of course, primarily here, but if you simulate it, you see that it also goes there, and there is a tiny gradient. So if you're starting to try to see very small things, you see that from the parasitics, there is no reason why the field would be fully homogeneous and shake.
Sure.
If you shake symmetrically the two source drain, it's equivalent to a gate. But then if you start to shake a bit asymmetrically, so we worked out with Andre and Matthew in details the theory of exactly the microwave response, so this is how we can tell that it's mainly the gate.
So how hard is it to create junctions, like T-junctions or things like that, in terms of the
This is very hard. So I would say that if this architecture, so let's say with nanotubes it's very hard, but if now you tell me, I don't know, I have a 2D material which can be topological, I tell you, okay, but you can take my magnetic texture, which as you see there is a 2D structure, and you can imagine to do some control grading. If you have a 1D structure, you will need to rely on either grading in some kind of more you will have to rely on grading not in real space, but in some kind of parameter space or and then if you take T junctions of nanowires, then again you have some kind of 2D structure which you can essentially put on the on a magnetic texture, and it would work, I mean, exactly the same as
that 2D structure was what I was saying, that if you have
yeah, so with nanotubes, I think it's very difficult. I'm not sure it's going to work. But then let's say now we have shown that with this magnetic texture it works, and it gives very large spin-orbit interaction. Now, if you have better means for making a 2D structure than nanotubes, then people, of course, I mean, you can use it. So there are proposals, for example, for using this for creating a giant spin-orbit interaction in graphene. So, for example, I guess this would work equally with graphene, but I'm not sure graphene would, let's say, for topological things, it will help. But at least for 2D, if you have 2D conductors with topological properties, this would work as well. Yeah.
More questions? Okay, now let's thank the speaker again.